Okay, so here we're going to look at putting a regular old number, an expanded notation is what I like to call it, into scientific notation. We've already talked about kind of the format, or at least this has been discussed in the slides so far, about the format of a number in scientific notation. Okay, it's got some number, okay, times 10 to a power. Okay, and so we call this number here the coefficient. And just like we've used coefficients in balancing chemical equations, just like you use coefficients in math class, coefficients are the number that are in front, or they're leading terms. Okay, so it's the same thing here. All right, so you have your coefficient, then it's multiplied by 10, so times 10, raised to some power, and we're going to look at what this means here in just a couple slides. Okay, this power is what we call the exponent. Okay, so same terms you use in math class, we're going to use them here. Scientific notation is not some fancy thing that only chemists use. So let's just kind of do a refresher. Most of you guys may have already learned this already. Okay. So the way that you end up getting this is by moving your decimal place. Like here we have an absurd number of digits that just really aren't significant. Okay, if I have 460, whatever this is, okay, most of you guys, that's all you're going to stop at. Changing numbers down here, you know, in your like hundreds and thousands and millions and billions and trillions, that's not going to change the magnitude or how big this number really is. So instead of having to draw out all these different places that don't mean really anything when it comes to your number, instead we move the decimal place where we can really look at just that 4 and 6 and really see how that's related. But we need to make it the same number. We need to still express that it's, you know, 4 and a 6 with a whole bunch of things behind it, that this is a really large number. So we're going to say how many times do we need to multiply this coefficient by 10. Okay. Well, we also know that every time that you multiply by 10, you move a decimal place, right? So if I were to multiply this by 10 again, I would add another 0 at the end. So going to keep that in mind while we're working these problems. And to go from expanded to scientific, you got to find where your decimal place is originally, and you're going to kind of work your way backwards. All right, so I'm going to use orange. So my decimal place is there in purple. Okay, I had to move my decimal place 1, 2, 3. Excuse me, I had the hiccups. So 3 times, and instead of going, you know, each and every single one, I've got 3. There's 6, 9, 12. 15, 18, 21, all right, now we're here, 21, 22, and 23. So for our purposes, and you might see scientific notation written with more than one digit in front of a decimal place for the coefficient, but you know, for our purposes and for the kind of an accepted way of representing numbers in scientific notation is to have only one digit in front of a decimal place, the rest go behind. So we're going to move this as many times this way to where we have a number between 1 and 10 as our coefficient. So 4.6 is between 1 and 10, 46 is not, neither is 0.46. So that kind of helps guide your decimal place to be behind only one number. Okay. So we had to move it 3, 6, 9, all the way up to 23 times. So we write this as 4.6 times 10 to the 23rd power. Okay, and again, this means that I'm multiplying it by 10 23 times. And well, if I multiply it by 10 one time, now I've got that. I can bring it 23 times, or multiply it by 10 23 times. It's going to move my decimal place down here. Okay. Now, another thing too that we haven't really gotten to focus on much is that we've got units now. Every number is, I call it a naked number. It's meaningless unless it has a unit. Okay, you use numbers to count, you use numbers to measure, and unless you say what you're counting or what you're measuring, you're just, it'd be like walking into a room and being like, 4.6 times 10 to the 23. Nobody knows what you're talking about unless you say, you know, what that unit is. So in this case, we were looking at the Hope diamond, and this big old number here, which is easier to say as 4.6 times 10 to the 23rd, that's actually the number of carbon atoms inside that diamond. So it's an absurd number of atoms. And so, you know, instead of walking in the room and saying 4.6 times 10 to the 23, now I'm going to say 4.6 times 10 to the 23 carbon atoms. So there's this many carbon atoms, in this case inside the Hope diamond.